Okay, so I just got the live stream started, so I wouldn't forget. Got it on speaker view. I think we're all good to go. Obviously, I'm waiting for this thing so I could hit pause. But where were we last time? I think we're about page 130. Yeah, we're going to start up on page 130, all right? So our goal for today, we want to finish RC transients. We're going to spend about an hour on that, maybe 45 minutes if I'm going slow. All right, and then we're going to start force magnetic. So we're going to start magnetism later today. All right. All right, and so we talked a little bit about these last time. So I'm going to go ahead and start with the problem, and let's just start with problem 27.21. And we'll try to remember some of the things we talked about. So just so I have space, I'm going to get rid of this. All right, so we have a circuit here that looks like got a battery here. What number did I say this was? 27.21? Yeah, thanks. There's a switch here. I think we're told this is position A. There's a capacitor here. That's it. Right? And then over in this other branch, give ourselves a little bit of space there. Now we have room to write crap in here. And let's see, this is 2R, this is C, this is battery, so I'm going to assume that's E, and this is just R, right? Okay. It's in this position for a long time, right? It's in this position for a long time, and then I guess what's a name for this picture? Do you remember what we called it last time? T equals. No, that was tau. The time got. What did I call this? Was it the
Infinity?
zero? No, infinity is after the switch has been thrown a long time. So this is 0 minus, meaning just before we flip the switch. Is that good? This was the 0 minus picture, right? So the next picture would be what? T equals 0 plus. And I'm just looking at this. I can tell I'm going to run out of room a little bit. So I'm going to scoot this over. Sorry. Just so I have room here. And then when I flip it over to position B, do you agree that everything over here is no longer in the circuit? When I flip the switch to B, I argue it's basically just this. R and C. Once I'm in position B, the idea is when I flip over to here, this stuff is no longer connected at both ends. Everybody good with that? Okay. So this is 0, and then let's go ahead and stick a T equals infinity picture on there. That just means after a long time. Still have a capacitor. All right. So now, let me see, what else did I say? Okay, switch is thrown from A to B. Okay, so we're trying to get the voltages and currents and charges and stuff. All right. So now in this case, let's go to the 0 minus picture. The switch has been sitting in position A for a long period of time. How much voltage is across C, or what do you know? I guess if it's sitting in A for a long time, what do you think about the circuit? What are your thoughts? Okay, so I heard the voltage across this capacitor should be E. Let's think about it like this. I just want to make sure I get the reasoning right, because that's going to matter in the next problems. Okay, so the reasoning matters here. Do you agree that once this thing gets filled up, no current flows? That's kind of the fundamental physics going on. This gets filled up and it's causing an electric field that blocks the current flow. So we expect capacitor fully charged blocks I, meaning blocks current flow. Well, if there's no current, how much current is flowing through resistor 2R? Some or none? None. If there's no current through this resistor, what's the voltage across this resistor? Yes. So we expect no voltage here. Now do KVL as you go around. Well, if this has no voltage and this has E, something better take up that E volts. What is it in this case is left? The capacitor. So you're absolutely right. The thing about it is, your reasoning is not always right. In this case, it was correct. This is what I want you to think. A fully charged capacitor blocked current flow. Got that? And then from the rest, use deduction to figure things out. Is that okay? All right. Do you recall what piece of information we're supposed to bring forwards from the 0 minus picture to the 0 plus picture? There was one thing. What's that?
The direction of
No. I don't want to go that way. It might relate to it a little bit, but no, not that's not where I want to go. So I would say no. What does a capacitor preserve? Capacitors preserve, what was the word? No, well, yeah, charge, but I think of them as preserving voltage. Okay, so that's the piece of information we needed to get to. That's why I spent all my time figuring this out, because that's the piece of information we can bring over to here. Now, I heard somebody say it preserves charge. I want to think about that for a second too. This is the plus terminal of the battery, right? The E. And this is the minus terminal. The plus terminal is going to attract electrons from the upper plate. So the upper plate of the capacitor, do you think it's going to be positive or negative? This is positive. It's going to attract electrons. What's left? Plus. This is going to be positive up top. It's going to draw those electrons off and pump them around. Now, current is flowing the other way, but so if you're curious, let's do a quick KVL. Right? When I go here, you see how I exit on the plus plate? So I would add E. Then here I exit on the minus plate. I would subtract E. Looks good. All right. So you could argue that that charge doesn't have time to move at the instant you flip the switch. That's like saying it, I would say it preserves its voltage just because that's what everybody says in the business. All right. So that's what we're going to say. Well, so that is the first thing. If you're taking notes on this, put a number 1 next to that. Right? That's the key to solving these types of problems. What's something else you can figure out after you know that the voltage? What's something else? Anything else? Current. Oh, how are you going to get current? Oh, well, to get Ohm's law, we need the voltage across the resistor. We don't have that yet. What is the voltage across the resistor? How do you know? Okay, so he said, because this is in parallel with that, now I know this must also have potential difference E. And then you said, oh, I could get the current, right? How do you get the current? V equals IR. So in this case, what's the current? E over R. And if we needed it, what's the charge on this thing? It's so EC. All right. Now, again, I want to emphasize the first piece in making all of this work out was getting that voltage of the capacitor. We got that from the 0 minus picture. That's all this picture is good for. Because the capacitor preserves its voltage, we spend a lot of time figuring that out, and then the rest is using logic, KVL, whatever, parallel series, any kind of rule you can think of. All right. After a long period of time, what's going to happen? If you let this capacitor, which has some energy stored in it, and connect it to a resistor, resistors do what to energy? They generally tend to dissipate that energy as heat. They get warm. Remember the wires heat up? Basically, the resistor is going to chew up all that energy. So what's going to happen to everything in the end? Get a bunch of zeros for everything. Got it? All right. Now, we've done that. It says next, determine the energy stored in the capacitor as a function of time. Any ideas? I want to get energy as a function of time. What's the symbol for energy? Remind me. I want U as a function of time. Any ideas how we might approach that? Remember what we did last time? You guys hear me on Zoom all right? You can see everything okay? Ooh, it's a little off.
Yes.
That's close enough. Do you remember that general equation I gave you last time, the x of t equation? It's on your equation sheet if you want to flip to the back. You remember that equation? It was x of t equals some crap.
Yeah.
X final plus, what was it? X initial minus X final times e to the negative t over tau.
Yeah.
Where tau was equal to RC. Remember that? It's written on your equation sheet, so you don't have to, but that's what we're talking about. If I want to get energy as a function of time, what do you think? Could I just get the energy initial, energy final, and plug in?
Yes.
I see someone shaking their head no. Why not?
I just remember that that's something for slowly or during.
Yes, this is valid for first order differential equations or linear ODEs. Now I'm just going to put out an equation here. You guys remember that U is something like Q squared over 2C, or sometimes we said it's 1/2 V squared C. See how this is nonlinear? It's got a squared term in it. Or right, like think about power. Isn't power something like I squared R or V squared over R? That's nonlinear. So PU, don't use this equation for PU. All right. So that was good. You remembered correctly. But what we could do, well, I just erased it. What's the equation for the energy in the capacitor that you might want to use? Which one of those do you want to use? How about Q squared over 2C? Do you agree that's the equation? This equation is valid for Q, isn't it? So couldn't we just use this and figure out Q? Let Q equal X and plug in, where do we get the initials from? Which picture do we get the Q initial from?
0+.
So 0 plus. Yes, excellent. This is the initials. These are the finals. Let's pop it in there and what do you get? So that's the, okay, so big picture, that's how you do this. If I asked you to get energy as a function of the time, you do this, 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 then you'd say, I could use this to get Q as a function of time, then I plug it into here and I'm done. That's the goal. Since we're so close, let's plug this in. And just so I have room here, what I'm saying is Q as a function of time is equal to, what's Q final? 0. Q initial, EC. And then tau in this case. Is it going to be R? Is it going to be 3R? Is it going to be 3/2 R, 2/3 R, or what? Does the 2R matter, do you think? No, not for this part of the problem. Do you agree it matters not at all? It's not even in the loop. So here, do you agree it's just a straight up RC? So far, so good? Well, that's just, I'm going to show you something that maybe you have seen before, maybe you haven't. A lot of times when you get a lot of exponential crap, people start writing this. EXP with brackets. EXP means exponentiate anything inside the brackets. So this means this is the same equation. It's EC times E raised to that stuff. Have you seen that before in your math classes a little bit? If you haven't, this is just a different way of writing it. It gets kind of nice if you have really long exponents. So I thought I would mention that. Sometime, by the way, take a guess what function you would use in Excel if you're trying to exponentiate something. Equals EXP, and then you type it in. So this is common in a lot of languages. If you're coding, that's how you type the E to the. All right, is that enough on that? Standard function there. All right. So at this point, I could plug it into here, and what would I get? Let's finish strong. I'm going to get a 1/2. When I square this, what happens here? I get E squared, C squared, and then I divide out one of the C's. So that's going to be E squared C over 2. What happens when you square this? Yeah, we get EXP negative 2T over RC. Notice it's a little bit different than if we had just used this equation with U. The equation with U, you might think you'd get it right, but you'd be off basically in your tau. Yeah. All right. What do you think? So far, so good? Now I keep alluding to this, and I keep telling you that this 2R doesn't matter. But in what sense does it matter? Right? When would the 2R be involved in the real world? You tell me. Under what circumstances would the 2R, maybe it helps to have a real circuit, right? So here's the real circuit. Oops. Oops. There we go. All right, so here's the circuit. We got our battery here. This is one of the resistors, right? Notice I flipped the order of the battery and the resistor, so what? Then here's the capacitor. Here's the other light bulb over here. Unfortunately, I don't have R and 2R here, right? When does this light bulb matter? When it's charging or discharging? Charging. Charging. So this 2R in our circuit up here, wherever that was, the 2R in the circuit actually matters when you're charging. In particular, this is what I'm wondering. Based off our circuit here, should this charge or discharge faster? Well, in this case, right, the idea here is, there we see it light up temporarily, and then here we can see it discharge, right? When the two light bulbs are identical, it should charge for about the same time as it discharges, and that seems true. Now let's go back to what we've got here. On this problem, which is going to happen more rapidly, charging or discharging? When I'm in this branch, it's charging, right? When I'm in position A, the circuit's charging. What's the time constant?
negative T over 2RC while charging?
Just the time constant. The time constant is just the amount of resistance and the amount of capacitance. So what
Oh.
is that?
2RC.
2RC. When I'm discharging, the time constant is just RC. So based off that, which time constant is bigger? Charging. So which takes longer? Charging. That's what the time constant's all about. So the time constant is kind of like, oh, which thing takes longer? Everybody good with that? That's all I was trying to get at. So the 2R does make a difference when you were charging, but it just didn't happen to matter in this particular problem because we were worried about discharging. So far, so good? Sorry if I made that more confusing than it needed to be. Take a look at problem 27.22 in your workbook. Is that the same problem, basically? What's different about that problem in 27.22? So for reference, I'm going to draw it up here. So this is 27.21. 27.22 looks nearly identical. There's a battery here. There's a switch here. There's a capacitor here. 2R. R. And okay, there's a capacitor here, C, there's E. Which is going to happen faster in this circuit, charging or discharging? What do you think?
Charging.
Why do you say charging? I still have this 2RC here.
When charging, only the 2R is there, but when discharging, 2R and R is there.
And they're in series or parallel?
Series.
Series. So what's the equivalent resistance now? 3R. So I just wanted to point out, these two circuits look nearly identical. And so on your test day, it's going to look nearly identical to something that you've seen in the workbook, right? I love me some RC transients because there's a lot of thinking involved. So you know this is coming. It's going to be on the next test too, and it's going to be on the one after that. So 3 tests in a row of some kind of thinking like this. So if you've got to get good at something, this is a good idea to get good at this. All right, make sure you do these problems because I always, and I'll talk to you more about this in the next 30 minutes. Watch out. You can't really take shortcuts. You've got to think it through and do some physics, and I think that's why I like it. So I'll leave this one for you to do at home. That way you got one to do. Let's take a look at 27.23. All right, so I'm going to zoom out here for a second. Looks the same, doesn't it? What do you think? Is it or is it totally different? I'm going to say wildly different. What's different? The switch position, right? Okay, so when you look at this one, and this has E, I just wanted to have all 3 up here at once. Can you guys see all 3 at once on Zoom? I'm going to zoom in a minute. Let me just do this. Just so you can see all 3 at once. Can you see that kind of online, people?
Yeah, that's good.
All right. Notice there's differences in each of these. Here, I move the resistor. Here, I move the switch. And my claim is this dramatically changes the physics required and the understanding required. All right. In particular, when you close this switch, which resistor matters? Both of them are somehow in the circuit, right? So we may have to think about both of them. This is very different than either of the previous two. All right. So we're going to analyze this one. And what I want you to do is try and get some infinity pictures and 0+ pictures. Well, let's start simple. In this case, now I'm going to go to just that board. And I'm going to go just a little bit out just in case I need it. All right. So in this case, it's open for a long time. What's the one piece of information I need from this image, this 0- picture? There's only one thing I need. What is it? Voltage where? Past. If it's open for a long time, what's up with that? What's the voltage?
0.
0, right? That's the same thing as saying this, right? This switch is open for a long time. This one's closed. This light bulb has plenty of time to dissipate all the energy. The new word is, rather than dissipated, is power is delivered from the capacitor to the resistor. Just say delivered to. When I grew up, it was dissipated. My bad. All right. So next, let's get the next picture. And actually, I'm going to shrink this one down a little so I have some room. Sorry. You don't need to do this. Same picture, I'm just shrinking it. All right, so that gives me more room for the pictures that matter. You know what I'm saying? And we said the most important thing was that the voltage across the capacitor was 0. All right. Switch is closed. Still got our capacitor here. We've got 2R here. And we've got R over here. All right. Walk me through it. What's the most important thing? Where do we start? What is it? Voltage on what? Where do we start? Which? On the capacitor. We always start there for capacitor transients. Okay. What else do we know then? That's the first piece of the puzzle. Tell me anything else we know. What's that? C and R are in parallel. Okay. He says C and R are in parallel. What does that tell us? What do we know about things in parallel? They have the same voltage. So what is the voltage across this resistor?
0.
Yeah. Well, what does that tell us? What about the voltage across 2R? Yeah, how do you know that? By KVL, how about I say it that way? Meaning voltages around the loop. What about the current? What's the current over here? How can you tell? Yes. We take the voltage across this resistor, which is 0, divided by its resistance to get the current through that resistor. What's the current down here? The current through the 2R resistor is, what's the voltage across that resistor? Over that resistance, yep. So he said it was E over 2R. So the current through here is E over 2R. Now think about it. What we're saying is, when you first flip the switch, this capacitor acts like a short circuit. You see it? That's good reasoning. If a capacitor has no charge on it, it acts like a short circuit. Look. Watch this bulb, right? My claim is now this switch is closed. It's the same circuit. When I hit this, watch that light bulb. Did you see it didn't light up right away? It took a second. All right, so yeah, there we go. Again, it takes a second for it to light up. When I first throw the switch, the instant after 0 plus, there's no current through it. We're good. All right. That's pretty much everything there is to know about this, right? How about the T equals infinity picture? Man, I'm running out of room. Shoot. I'm just gonna squeeze this in here. That was 0. All right. I'm gonna just stick this capacitor right here. I think that's still showing up on Zoom, right?
Yeah, you're good.
Okay, thanks. And I just had to make some space so I have some room to write crap, that's all. All right. Where do we start every time with this type of, which element do I attack? Capacitor, excellent. What do you know about the capacitor after it's been sitting there a long time? What's going to happen to it? We're charging this time. So it's going to, right? Because this time, before it was like this, we flipped it over here and we got rid of the battery. That's why it was going to 0. This time, do you agree the battery's still in the scene?
Yeah.
So what's going to happen to the capacitor over time? Fill up. It's going to hit full charge. What does the capacitor do when it hits full charge? There's no current flow. So where does all the current go? In the outer loop, agreed? So this is our first piece of information. No current. This is our second piece of information. The direction the circuit starts flowing. Or the direction the current flows. Sorry, not the circuit. So what is how would you attack it from here? Give me anything you know. I know this battery's weak. What would you do now if you want to figure out all these voltages and crap?
The voltage on the resistors.
Okay, how would you get the voltage on the resistors?
Well, it's not going through C, so the voltage on R is just E.
Nope.
No.
Oh, there's series, right? So what's the equivalent resistance? 3R. So what is the equivalent current? E over 3R. So what's the voltage across resistor R? It's the current, which is E over 3R times the resistance. What's the voltage across resistor R? E over 3 in that weird kind of psychedelic script E. That's always the weird one to me. Does that make sense at all? Jacob, you good?
Yeah, I didn't see it was in series.
No one does at first, right? That's why we're doing it. Okay, does that make sense now? So wait a minute. If we know this, how could I figure out the voltage across 2R? Could I do the same thing? Are you guys tired? Yeah, you could do the same thing. Isn't it the same current? And do you agree you're going to get 2/3? Right? Or could you do KVL and say, look, this plus this had better add up to E?
Yeah.
Either one of those. Well, wait, what's the voltage across the capacitor then? What?
0.
What? No?
Oh, see.
What's the voltage across the capacitor?
0.
No,
E.
not E. How do you know it's 1/3? In parallel, things in parallel to say. So I just wanted to point out, students have this tendency to always just guess 0 or E, and that doesn't work. Okay, so now you know why we did all three of these problems. I think that's enough on that. Do you agree? Moral of the story. You have to understand these pictures and think and use a lot of physics. What is the key thing what was the first piece of each circuit we had to attack every time? We don't get a choice. The capacitor, the capacitor, the capacitor. We start from there, then use logic and physics. Okay? Good enough? Yeah, question. Yeah. The capacitor is not in parallel with E, is it? It looks like it until you realize there's a resistor down there. It's in parallel with this combination. Well, think about it. If I redrew this one, you could maybe see it better. Maybe that's what you guys were thinking. I don't know. Right? The capacitor is in parallel with that. And then in parallel with this other resistor, right? Well, keep in mind, this one had voltage E. This one had voltage 2/3 E. This one has 1/3 E, 1/3 E. It all works out because we lose 2/3 here. So this is 1/3, 1/3, 1/3. Got it? Is that what you needed to see? All right, all right. Yeah, this is not in parallel with that battery, but it is in parallel with that. All right. Again, one last time here, just showing you this. The idea is, in this case, we expect if this switch is closed, this is just the same exact circuit. When I drop this one starts bright. This one starts dark. Once this capacitor gets filled up, it starts blocking the electric field in this branch, which causes all the current to go through there. And so this one should actually get, what happens to the voltage across this bulb here? What happens to the voltage to this one? Does it increase, stay the same, or drop? It drops. So this bulb is actually going to get a little bit less bright as this one gets brighter. Ready? I don't know if that makes it any more dramatic, but it sounds cool. Oh yeah, did you see it? It actually does everything we expect. Now keep in mind, this is not an exact model because these two light bulbs are pretty close to the same. So I would have to have actually put in 2 light bulbs here or something, but whatever. It gives you the idea, okay? All right. All right, so we've seen a couple of types of questions now. We saw ones like this first two right here, where we could get functions of time using the x of t equation, right? Remember that? We found current as a function of time or charge as a function of time, something like that. And then we could use that to get energy or something. And then we could use that to solve for time or resistance, whatever. We saw a second class of problems. I don't know if you realize this, but this is a totally different type of problem. It's a little bit tougher. This one, all we can pretty much do is get the 0 plus and infinity pictures. Now, here's the issue. What is the time constant for this circuit? Am I going to use R? Am I going to use 2R? Am I going to use 3R?
Three R.
You're going to use 2/3 R. And most of you probably would not see that. Agreed? From the capacitor's perspective, is this resistor in parallel with that resistor? This is beyond the scope of this course. If you look below problem 27.23, there's a long, boring diatribe from yours truly explaining this is not what this class is about. My point being, when you get one of these questions that's like this, I'm not going to make you get the functions of time. because seeing the time constant takes a little bit of extra effort, and that's beyond the scope of this course. Got that? So, question 27.24 gives you another one of these to practice at home. I did all these gory pictures on the solution, so you have one. Make sure you do 27.24. So there's two types of RC transient questions. Got that? There's these ones where we get the functions of time. There's these ones where we figure out the current and whatever voltage for the 0 plus and infinity pictures. What's the next type? 132. Oh, graphs, your favorite. Everyone loves a graph. Take a look at 27.25. See if you can figure it out before I get there. I'm going to erase the whiteboard and get to it. Looking at 27.25, page 132. I'll erase it. And you can talk as much as you want, or, you know, this is the weirdest class ever. You can also just chill, whatever works for you. Okay. Okay. Ten, 20, 30, 50, 1, 2, 3, 4, 5. Grid lines are not generally standard, but for what we're doing, it helps to have grid lines so you can see. So that's why I tend to put grid lines on there. All right. Anyways, okay. We're told we have an RC circuit, I think. And we're told that R is 1.00 kilo ohms, I think. All right. We don't know what E is, and we don't know what C is. We're supposed to figure them out. Believe it or not, this is really darn standard. This is something electrical engineers and people that work with circuits do all the time. Later on, we're going to learn, this is a graph of voltage versus time, right? That's basically like a DMM, right? DMMs can measure voltage, except instead of just giving you one number, it's going to print out a screenshot. This device that does this is called an oscilloscope. We're going to use them later this semester. So an oscilloscope gives you plots of voltage versus time for circuit components. This is very classic here. Now, part A says figure out the voltage of the battery, right? Sometimes we call that script E. What's that gonna be and how do you know? 5. How do you know it's 5? Just tell me, what's your reasoning?
It reaches 5 and levels out.
We call that asymptotic approach, right? It's asymptotically reaching 5 volts. So you can just tell it's going to 5 volts. Well, we know that the capacitor generally reaches the same voltage as the battery. So that was it, not anything clever. It's reading a plot. So far, so good. Part B, what are we supposed to figure out? Capacitance? Well, how would you attack it, in your opinion? You agree we need some kind of equation that has C in it, all right? Can you think of any equations that have C in it? Okay. Actually, what does this curve represent? What does this represent? What did the problem give us? What is this?
Voltage over time on the capacitor.
Voltage as a function of time for the capacitor. Isn't that what we have in our picture? Huh. Do we know anything? Does that
Can we
make
use that equation from earlier?
what equation? Yeah.
The shoot, the voltage final
Yes,
plus
okay.
yeah.
We could write down well, in this case, if we're trying to do voltage across the capacitor, right? What's the final voltage going to be?
5.
5. Or are you okay if I just write E to save myself a little space? E, which is 5. Exactly right. What's the initial voltage? 0. Right? It's 0. Well, that's just So in this case, we've got that. How does that help us get the capacitance? Where does capacitance show up in this? In that tau. What's tau? Do we know what R is?
Yeah.
We're looking for C. Do we know what E is? So now, how do we get the job done? I'm just going to write this up here so we have it all in one place. How are you going to get the job done? What's that? Yeah, that's what I'm asking you.
50.
What's that?
Use 50.
No. Okay, and this is what I wanted to point out. You would think, can I use 50? Right? Because you're thinking 50 might be 5 tau, right? You might be wrong. Here's what I have learned, and this is true in a circuits lab too. Generally speaking, you want to pick times in this sweet spot in here, where it's not all the way up and not all the way down. The reason is your answer had better be within 10% of my answer, or you don't get credit. Right? And generally speaking, we want to get numbers right within 10%. That seems reasonable, right? So the idea here is if you pick a number close to 0, your error in time could be huge. If you pick a number close to 5 tau, your error could be huge because we're getting this subtraction here. And so then it turns out this creates a huge error if you pick too close to 0 or too far from 0. You want to pick something in the sweet spot. So look at the graph again. What would you use? 8. Or what's the other one?
10.
Yeah, 10, it's hard to read the voltage. Do you agree? You could argue 6 as well. Do you agree? 6, but that's also hard. What's the other one that lines up exactly on a grid line?
12. No, 14.
Yeah, so I would use 8 or 14. And so the idea is you pick a set of points, and I think most of us really liked the 8. Do you agree? Because at 8 seconds, you know, or at 8 microseconds, check those units, the voltage was 3.00 volts. So the thing that students forget is you got to pick a time somewhere in the middle. Does that make sense? Yeah. People love to say, oh, 5 tau is 50 on this plot. And it turns out, I don't think that's right. I don't think 5 tau happens to be 50. It just kind of looks like it. But you can't tell whether it's at 0.97 or 0.98 or 0.99. And so you could actually introduce a huge error there. So far, so good? All right. So obviously I could do the same type of problem with the current graph. And that's the main types of problems that we see. Basically using a graph to get the information or doing the other 2 problems that I showed you earlier today. Is that good? All right. So let's go ahead and take our break now so I can get some demos ready for the magnetic fields. I guess before we do that, are there any other questions about capacitance? Ooh, I just love them. I just want to make clear, I don't remember if I said this. I love these kinds of problems. They're going to be on lots of tests. So make sure you do these problems and study them well. I think there's a lot of physics to be learned. So it's going to be on this test. On the next test, we're going to have what are called RL transients with inductors. Very similar, but inductors preserve current because they use magnetic energy. And then on the final, I almost always throw in one of these, either an inductor or a capacitor. So we're going to do it over and over and over. All right, let's take that break. Any questions from Zoom before I hit the break?
I'm all good.
Okay. Yeah, right on. Is it getting kind of close to the time, everybody? Getting close-ish? I'm gonna go for it. Oops, wrong way. Old school. All right, so I think we're streaming. You guys are out there. You guys recognize what that is there on Zoom?
Looks like a monitor.
Yeah.
Old CRT monitor.
Oh, yeah, look at this. Look at this gem here. You like that? So let me plug this in. So you might be wondering why I'm bringing this up. Somebody called it a CRT. Does anybody know what CRT stands for?
Cathode ray tube.
Cathode ray tube, right? Hopefully there's something showing up there. Can you still see it? Is it in the screen zoom?
Yep.
Is it starting to fire up? Okay. Let's get this here. Give it a second. Come on, computer. Oh, did I accidentally shut it down? Oh my gosh. Well, whatever, you can see something here. Here in my hand, I have a magnet. It's gonna, oh, come on. Oh, all right, well, I guess we're still on break. There we go, come on. Okay, what's gonna happen when I bring this magnet close to the screen? You guys see some colors showing up there?
Yeah, that's crazy.
So why is it doing this? Do you know? How does a cathode ray tube work? What does this pattern remind you of? Does that pattern look vaguely familiar?
Looks like the electric field.
Oh, you got it. Was that Christian?
Yeah,
What electric field?
like the simulation one. I'm not sure.
Yeah. It was two charges. Remember? That's what.
Right. Yeah.
Yeah, electric dipole, right? Doesn't that
Yeah.
kind of look like? Well, this is a magnetic dipole, north and south. So instead of plus and minus, we got north and south. All right. Weird is if you turn it on the side, you kind of look like this quadrupole. You see four of them showing up?
Yeah.
See that? It's hard for me to hold this and get out of the way, but it looks kind of cool. So the idea here is, oh, and then I don't know if you can see this, but you see this LCD here or this laptop screen?
Yeah, I
Right?
can see it.
We don't see this happening over here, right? There's a fundamental difference. What is it? So let's go to the board. The idea is, well, here's a cathode ray tube. Let me draw that first. So you take a tube made out of glass. You don't need to write this down. Right? And then inside is a vacuum, or as close to a vacuum as they can get it. All right? So there's some vacuum, and inside of here, they take two pieces of metal, a cathode and an anode, right? And then let's try to make this look more like a TV here. The idea here is this is the screen. There's a little bit of phosphorus here. Usually, different designs. So this may not be our exact design, but so there's a phosphor screen there. The idea is, in this case, we could have an electron sitting in here, right? And this electron is going to fly this way. So maybe what we do is we put a negative voltage on this and a positive voltage on this. And maybe instead of having this just be a wire, maybe you'd have this be a grid. So there'd be a grid voltage. Remember? Yeah, you know what I'm talking about. So, right, you could have this electron, you could heat up a wire and have it spit out electrons. And then they're pushed away by this electric field, right? And they come launching over here. Well, now at some point, you put a magnetic field in here. let's say there's a magnetic field into the page. And the magnetic field is going to be the symbol B, all right? Well, in this case, what's that going to do to this electron? We know there's a magnetic force. This is the new equation we're learning now. Q V cross B. So the critical thing in the magnetic force is we need to have a moving charge. Right? And so in this case, the cathode ray tube creates a beam of moving charges, and that's why we see it being affected by the magnet. Got it? All right. So in this case, does anybody remember how you do cross products and figure out the direction of the force here? What I'm wondering here is when I put this magnetic field here like this, is that going to cause this beam to deflect up, down, out, in? What do you think? Let's go through it. I have a cross product. Does anybody remember any right-hand rules for any cross products ever? Line up your fingers with the first thing. Curl them to the second thing. Thumb points in the direction of the output. Right? So first goes to second, goes to output. Now in this case, this is the velocity direction. Do you agree? I'm going to point my fingers in the direction of that velocity. I curl my fingers to B. Which way is my thumb pointing? Up. So what direction is the force? Down, because it's a negative charge. Don't you love it? I'm such a cruel bastard. All right, so in this case, because this charge is negative E, that's going to flip the output. You see what I'm saying? So V goes to B, thumb points up. Oh, it's a negative charge. That's going to flip the force to downwards. This electron is going to fly through here like this. And the idea is how an old cathode ray tube works is you could have a variable B field or a variable electric field, basically, and have this thing go up and down. You could have another one to have it go left, right, and you just go trace it out, and that's how they make these little patterns. It's amazing they work at all. And then to get colors, right, you need to have red, green, and blue pixels be energized. And so you need to be able to aim the beam precisely enough to hit the different colored pixels, right? It's crazy. It's crazy when you think about it. Mind-blowing. All right, anyways. All right, so this is what we're going to talk about next. The force due to magnetic field. Got it? So in this case, let's go to page 137. Right? So a couple of quick notes before we get ahead of ourselves, all right? So generally speaking, I think I try to use the blue color for B. That means external magnetic field. The units. The Earth's magnetic field has a magnitude of about 0.5 Gauss. All right. And it turns out 10 to the 4th Gauss equals 1 Tesla. So the units are going to be Gauss or Tesla for magnetic field, just so you know. Tesla like the car company or like the Nikolai. All right. Now for reference, a lot of times an MRI, the B field used in an MRI machine could be anywhere from 0.5 to 1 Tesla, 10,000 times bigger than the Earth's magnetic field. Interesting side note, the Earth's magnetic field cannot be ignored in a lot of real world situations. Obviously, there's some animals that navigate by magnetic field, right? However, the other thing is I like to think about submarines. When they're being built, submarines can acquire a huge magnetization from this tiny field from the Earth. That magnetization can be enough to trigger mines and cause everybody on board to die. So one of the things that they do with submarines is they'll actually put them inside a big set of coils and demagnetize them or degauss them. So just like these old monitors have a degaussing system in it, you can click a button and get rid of the magnetic field. We could do that at the end if you want. Those old CRTs, you could degauss them. You could do the same thing with a submarine. It's just a lot harder and more expensive. Okay. Oh man, there's some crazy pictures of levitating frogs with magnetic fields. Have you seen that? Yeah, we can get to that later. Maybe later on we'll do magnetic grapes. We'll show you how grapes can be magnetic if you just use a big enough magnet. It's crazy. It's subtle. It's hard to show, but we can do it. Pretty much everything is magnetic at some level. So we'll come back to that later. For now, these are give you some ideas of the units, the symbols. Any questions about these symbols right now? That's everything I want to say. Right? You could actually get up to like 20 or 30 Tesla, I think, at least 20 Tesla in the lab, which is crazy. But those are very small spaces usually. So in the bottom of a cryogenic fridge, yeah, whatever. All right, whatever. Now, let's take a look at this. What are the units of force? Newtons. What are the units of charge? Coulomb. What are the units of velocity? Meters per second. Which of these units do you think is the standard, Gauss or Tesla? We use Tesla. All right. So now, okay, we see that a Newton is equal to a Coulomb times a meter per second times a Tesla. I have a question for you. Most of the time in life, do you have electron beams flying all over the place? Like we used to in every house, you used to have one of those. Not anymore, right? Most of the time, where do we get moving charges?
An electric field.
I'm trying to think of a way that I could make charges move around. Any ideas? Circuits.
Circuit.
Wires. Do you agree that charges move inside of wires? That's where I was trying to go with it. Well, wait a minute. Let's just rearrange the units and get spicy here. What do we typically have in wires? What is our measure of moving charge in a wire? Amps. How does amps relate to these units? A Coulomb per second. So a Newton should be equal to an amp. What's left over? Meter times Tesla. What would be the equivalent force equation? What has units of amps? The pirate says, I, matey. I, what's something that has meters? Length, Tesla. Turns out these are equivalent. Sorry if that was a bad way to explain that. Right? Magnetic force. This chapter is all about magnetic force. Just like chapter 21 was all about the Coulomb force, this chapter is all about the magnetic force. Now, I just want to point out a more general equation of this would be let's color this blue for once. The idea here is, in general, if you have a wire, okay, this is your wire, ds would be a small segment of that wire. That's a small length. How do we get the direction of it? Do you remember what I told you about the direction of ds? Probably don't. If current was flowing this way, right? Current can't have a direction because it's technically not a vector. And have you noticed I'm pretty bad about changing back and forth between capital and lowercase? Let's try and be consistent. Sorry about that. Sorry. In this case, ds points same direction as current flow. So notice that can change depending on which part of the wire you are on. I would never do this problem to you because I can't do that problem. All right. I guess I could if I used a computer code, but yeah, I'm not going to do this. But the idea is, yeah, if you want, this is our general equation for magnetic force. At this point, I could argue we have finished this chapter. You know as well as I do, we need a lot of practice on this and some practical examples and see, where the rubber meets the road. Furthermore, there's something special that's going to come out in this chapter. What is one of the most useful applications of putting a magnet next to a coil of wire with some current running in it? This device is so hugely important that we give it its own special name. What's that? Well, an electromagnet actually looks like this down here. Hold on. This is an electromagnet, just a giant coil that you can run current through. This is actually basically a really messed up cathode ray tube as well. We'll talk about that in a minute. Right, just a big tube. There's not much air in there. There's going to be an electron beam in there. There's an anode, et cetera. Okay, but so that's an electromagnet. That's not what I was thinking of.
Is it radar?
Nope. Although that probably has all kinds of stuff in it that I don't know about as well. Would it help if I told you you're going to build one of these in lab this Thursday? Motors. Motors are hugely important in the real world, as you know. So what happens with a motor is you connect some wires to a battery or something, power source, and you get current flow. You put that current flow near a magnet and you get not only force, but also rhymes with fork, torque. And so we're going to be talking about torque, and that obviously is derived from the force. So yeah, that's kind of where we want to go with this. We want to understand forces on moving charges. We want to understand forces on wires, and ultimately use this crazy set of force equations to learn about torques on motors and things. Cool? And the same type of thing actually relates to chemistry a lot, actually. So if you want to talk about the torque on molecules, if you have molecules sitting in an MRI or something, you want to talk about, there's magnetic energy as well. And so, yeah, there's a number of applications. So just to be thorough here, turns out the torque is going to be something called mu cross B. Mu is going to be a magnetic moment. Magnetic moment is Ni area of a loop. You don't need to know this. We'll talk about it next time, okay? But the other thing is the energy associated with the magnetic particle is minus mu dot B. And so we're going to revisit these equations later on throughout the rest of the semester. That's why I don't want to focus on them right away. We'll get to this next time. I'm not sure when. But for example, this magnetic moment relates to the amount of current in the area of a loop. Let's just say it like that for now. So, right, you could imagine an electron in orbit traces out a small area. It's like current in a loop. It's not exactly right. It's off by factor 2, but blah, 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 blah. That's basically giving you your magnetism associated with a current flow. Right? Well, then you say, okay, if I know which way the current's flowing in an orbit, I can tell you how a magnetic field would affect that orbit. So this actually relates a lot to a number of different branches of physics, chemistry, etc. Exciting stuff. Good enough? Let's practice. Go to page 138. Let's look at 28.1a, and I'm going to erase this board. You can try and race ahead of me. Do whatever you want. I'm going to do the first one with you here. what did I say this is? This is 28.1A. So I'm gonna try and color code these just so I know my solution. So I've got a charge moving this way. There's its speed V. There's a B field. I'm gonna try and use blue for that. That's B external, B external. All right. I guess I could put an arrow on this. It doesn't matter, right? Whatever. You could have a magnitude in the direction, or you could have vector with the direction. All right. So in this case, I'm going to mention something here. I think in every problem we do, there's a cross product involved in this situation. I think we should know two things. Number one, our coordinate system. Let's put a coordinate system on here. How about we just use our standard one? I hat goes this way, J hat goes that way. What direction is K hat? How do you know that? Right. You know, now nobody else calls it this. I call it the wheel of pain. Right? But from cross products, you know that I cross J gives you K. So I, first vector, cross the second, output is this way. To remind you, a dot means out of the page. And what does an into the page mean? X. So for me, again, the dot is like the arrow coming out to hit you in the eyeball, and the X is like the feathers flying away from you into the board. So I just like to mention this stuff in case you want to do it with IJs and Ks. What direction is the force? I need a volunteer. We've only got 4 students here, so does one of you fools, one of you excellent students want to come up and try this out? Come on, help me out. I'll help you out. You want to try it? Come on. Yes, let's give him a huge round of applause. All right. Okay. So now we're going to try as a class to figure this out. So we want to figure out the direction of the force. What would you do?
B cross B.
Yeah. You want me to write up the equation for you, just to remind us? Force is equal to QV cross B. Yeah. So where do you line up your right hand to start? Good.
With B.
With V. Then just go ahead and leave it the way you had it for a second. Curl your fingers. Do they go to B, everybody? The way his fingers are curled, is that the way B points? No. So then notice what he did immediately. Go ahead. He's trying something else. Does that work? No. So then what do you need to do?
It sounds pretty, so it's that way. Then.
Okay.
Points down, but the negative charge. That's it.
I gotta check it. Go ahead. You do it and I'll do it too. So B goes to B, thumb points down, and then what did you say?
You flip it because it's negative charge.
Correct. So the force is up. Let's give him a round of applause here. All right. Thank you. That was the weakest round of applause ever. Okay.
Sorry, why did we flip it?
Negative charge. Negative charge. Flips the
Oh.
output. You see it?
Oh, okay.
Yeah, gotcha, didn't I? All right, so watch out for that one. Basically, gee, I wonder who tends to put negative charges on test questions. I don't know. All right, so you know I'm gonna stick a negative charge somewhere on there, just to mess with you. All right, so I think out of all this, didn't we say the force was up? I gotta check. So I just, no, yes, but negative. There's the force. Got it? Now, just so we have some room, let's go to the next one. What did I say? 28.1B. And then we did, is this going the same way it looks on the page? Yeah. Go ahead, do them all. I'll catch up. I gotta draw them first, okay? you can check with your neighbor or check with the solutions if you're waiting on me. Plus charge? Yes, okay. You guys keep going. I'm gonna get the other questions written up on the other board and then we'll talk about all of them. Okay. Force. All right. Okay, so we got this going here. All right, in this case, we talked about this one. How about this one? What direction is the force? On this one,
Is it upward?
let me see. B goes to B. It's a plus charge. I get downwards. You were close. This one's plus, so we don't have to flip the sign. Is that what you needed?
Yeah, that helped.
Yep. So when it's plus, we don't do the flip. All right, so that was good though. Huh, I'm seeing a pattern here though. Everything's at right angles. Everything's at right angles. So you got a 50-50 chance because you're thinking, okay, I've taken care of the z-axis, I've taken care of the y-axis, it's probably plus or minus. That's pretty good. How about this one?
I think it's like a 45-degree angle to the left, like with respect to the velocity. Yeah.
Yes, absolutely. Nice. So it doesn't have to line up on XY, but do you agree? If I could show these. The idea is they're still all at right angles. Oops. It's hard to hold these, right? It's still all at right angles here, right? I don't know if you can see that at all, but the idea is there's that one end of the page there. All at right angles there. Okay, good. How about this one? What direction is the force? .1.
parallel.
There's none. Remember that force equals QV cross B. Cross products pick off how perpendicular things are, right? Well, think about it in terms of this. This would be QV in the J hat with a, actually it's a negative J hat, right? Cross with B, which is B in the positive J hat. Well, what's J hat cross J hat? 0. In case you don't remember that, that's the magnitude of the first vector, 1. J hat has magnitude 1. Times the magnitude of the second vector times what for a cross product? Sine or cosine? Or cross product?
Sine.
Sine of the angle between. Well, what's the angle between J hat and J hat? How many degrees are there between J hat and J hat?
0.
0. Or you could argue J hat and negative J hat, it's 180, right? Well, what's sine of 0 and what's sine of 180? 0. Remember all that? Okay. All right. Let's go over here to the next board. Where was I? This was 6. All right. In this case, this is subtle. You're probably tired. You probably should pay attention a lot right now. Okay, here we go. In this question, this is very different, and I'll show you why. Trying to color code it a little bit so you can see it. In all of the ones up until now, we've always been given the 2 inputs and we're supposed to predict the output. Agreed? Now, what are we given? The output and one of the inputs, find the other input. This is a much harder problem, and I will explain why. But let's start simple and just kind of go with your gut. What does your gut tell you the options for the external field might be in this case? We see that there's a velocity into the page and a force up. In almost all the other problems, everything's been at right angles. So what is the only options left for B field if we were thinking that way? Left or right? So here's the trick. Start that way and say it's probably here or here. And then check them both. Which one works? Well, B goes to B, thumb down, positive charge, wrong. Do you agree this is wrong? So that can't be right. Because I just tried it and gave me the wrong direction. Let's try this way. B goes to B. Looks good, doesn't it? Ding, 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 ding. The problem is there might be another answer. In fact, there's an infinite number of other answers that are also correct. Okay, here's the issue. What if I plug in? I'm going to do a side problem. I think I got the room here. Sorry about this. I should have done this over here. I should have spaced it better, but I didn't. Okay, let's do a side problem. More 28.1e, right? The equation for the force is force equals, well, I've got, if this is our coordinate system, if we say this is I hat and this is J hat, out of the page is K hat, I double check, I goes to J goes to K, looking good, feeling good, being good. Force is good. In this case, V is, I get Q, V in the negative K hat, agreed? Yeah. Crossed with B, external, B, external. All right. So in this case, do you agree the general form of B external could equal Bx in the I hat plus By in the J hat plus Bz in the K hat? That could be true, right? Well. Keep this out of the way. In this case, what did we figure out about Bx? Was it positive or negative according to what we just figured out right here?
Negative.
So you just told me that Bx is equal to, how about I say Bx is less than 0? It's negative. Okay, what about By? Does By have to be 0 or could it be 0? Let's go over here and look. If I had a y component, V goes to B, that would give me a force to the right. Do I have a force to the right in this scenario? No.
No.
What does that tell me about By?
0.
By must equal 0. Well, what about Bz? Think about the math here. If Bz is some number and you plug it in, what happens to the k hat? What's k hat cross k hat?
0.
Yeah, so what could Bz be?
0.
Whatever you want. It's an infinite number of possibilities. Because Bz will never affect the force. And that's something that's different about trying to figure out the output of a cross or an input of a cross product. What we see here is this. The x component, the z component of the magnetic field would be parallel to the velocity and it would not cause any force. So there's an infinite number of answers. The B field could be this, right? It could be that, but it could also be that, or it could also be that. So you could have a component into the board, right? It could be pointing in this way, pointing out that way, almost out this way, almost anything between that whole stretch. Got it? What do you bet this is coming on your test? Because you have to think, right? So make sure you understand that. I don't know how else to tell you. All right. From there, I'll let you do the rest, okay? So just beware of that. Generally speaking, I like to ask these kinds of questions over here, where you get the output and one of the inputs, so you have to think. Is that clear? I'm trying to telegraph that. All right, you have to think a little bit. All right, now I want to go on to page 139. And I want you to think about it. It says, look at the motion of charged particles. In particular, I want you guys to look at case 28.2b. I'm going to erase the board and catch up, and I got to get a simulation running too, okay? So give me just a minute. We'll get the other board erased too. Try and imagine what that particle in question 28.2b is doing. You got a bunch of B fields here. What did I give you? A plus charge moving to the right or something? Plus charge moving to the right. I'll be right there to catch up. Just out of curiosity, you guys like it when I ask you your opinion on these? Would you rather have me do more straight up lecturing, or I try to ask probing questions, right? I feel like that gives you time to maybe digest and think. You can tell me afterwards if you prefer it, whatever way. But I'm
Yeah, I
probably
like
gonna,
it.
I'm gonna keep asking them no matter what, right? So I guess what does it matter? Well, let's start with this one. This, oh, what problem was this, by the way? 28.2B?
Yeah.
All right. What do you think's gonna happen? What direction is the force on this stupid thing? Upwards. All right. Is everybody okay that there's gonna be an upwards force?
Yeah.
So what's that gonna do to the motion? A second later, which way is it gonna move? It's gonna start to bend upwards. Do you agree? Then it's gonna be like, let's say it goes this way, it's gonna be moving this way. Just out of curiosity, if the force is perpendicular to the velocity, will it change the speed?
Perpendicular, yeah. Wait.
Does it change the, it changed the velocity?
Oh,
Does it
oh.
change the speed? Huh.
No.
Think about it. Probably not, right? Because, right, doesn't this mean there's an acceleration that's perpendicular to it? So, all right, more on that in a minute. We'll see. Okay. How about this? Once you're here, what direction is the force?
Perpendicular.
So just kind of describe it in words, or somebody in the class can point. Yeah, this way, right? This is the one that Christian did earlier, 21 or 28.1C or whatever, right? Okay, so then which way is it going to be moving? After this force, it's going to be moving more straight up. Huh, what shape is it going to trace out?
Circle.
Circle gets the square. You see it? It's going to keep bending, and there's a force towards the center of the circle. It's almost as if you just told me the force due to magnetism, magnitude, not vector, should equal, if it's going in a circle, what does it equal?
V squared over R.
Nope, but really close.
Oh crap.
M.
M, yeah.
You just told me that Q, V, cross B, and then take the magnitude of all that, is equal to M V squared over R. Well, in this case, do you agree that V is perpendicular to B? So you're going to get a sine of 90. I don't know if you can tell this, but this particular case is going to turn out to be QVB equals MV squared over R. The radius of circular motion is thus what? Solve for it. Move some stuff around and solve for this. What do we get? V drops. What is it? M V over QB. So depending on the parameters, this is called the radius of gyration, I believe, or whatever. You can read about this in a book. I'm gonna read about it in Python. That's how I feel. All right. Let's go this way, and let's go, whoops. Trying to get that. Can you see that on Zoom at all?
Yeah, kind of.
Little small?
It's just the lighting, but it's, oh, that's better. Yeah, that's fine.
Is that getting a little better? So I
Yeah.
can't show the whole code at once. You guys can see it out here too? Okay. All right. What do we got here? Your favorite. Just some boring cosmetic stuff, some boring stuff. Here's an external field. Well, in this case, what's our magnetic field direction? Is it in our example right here, wasn't it into the board? So let's just say this is 0, and then so the I hat is 0, the J hat is 0, the B in the K hat is like, let's say it's -1 Tesla. All right. So now over here, I've got a charge, it's positive, do you agree? Ball.q is a positive number. And then in this case, which way was it moving? It was moving to the right. Is that right? So its x component is there. And now here, okay, whatever. Maybe I'll start this at, let's start this at 0, -5, 0. Hopefully I remember what those numbers were. What were they? -10, 0, 5 or something? Probably, yeah. Okay. Let me just do this really quick. Hold on. Okay, whatever. I'm just gonna, we'll figure it out. Okay, so in this case, let's see what this looks like. Is that kind of what you expect? See that B field there pointing into the page? Right? Goes in a circle. Nothing crazy. All right. If I use a larger B field, what should happen to the radius of circular motion?
Smaller.
Let's take a look. Let's run this again. Okay, so notice that the circle is the same size as the axis. Do you see that? So that's going to be our reference. I think that axis is 5 long. What was it? The y-axis is 5 long. Yeah, so 5 above and 5 below. All right, so that's fine. So now if I use more magnetic field, we just solved that formula. B's in the basement. If I make B bigger, what happens to the radius? We use more force, we should be a tighter circle, right? Let's run it. Ah, yeah, that looks great, right? Smaller circle, it's half the size. We use twice the B field. All right, what if I go back? What if I use this same size field, but make it twice as fast? Whoa, that's a lot bigger, right? All right, is this working for you guys? Do you agree that it's taking these circular paths? Now, in case you're curious, here's the guts of the code, right? You recognize that right there? Q, V, cross B. That's it. And then we do our same tricks that we always do. If I scroll down here. Whoops. Come on. Trying to make this bigger. There, okay. Right, our same tricks. What do? We calculate the net force on the object. Then we update the momentum, right? Or in this case, velocity, momentum, yes, same thing. Okay, and then in this case, then we update the position, draw some stuff, and commit time. Same old, same old. Agreed? Right? Nothing fancy there. Now go to the next problem in your workbook. What's going to happen? We've done the boring case of when it's parallel, there's no force. We've done the case when it's perpendicular, we tend to get circular motion. What's going to happen if we have both a parallel and a perpendicular component? Getting a little bit smaller. Can you still see that on Zoom?
Yeah, we can see it.
Okay. So I put B in the x-axis now. I'm going to give the ball 0.5, and then maybe, I forget where I had it. I think it's here, 5. And then I think this was at -10. Comma 0,5. Is that right? I don't know. Let's see. I got it right. Is this the shape you expected? It's a spiral. Do you see that? The idea here is I put in a component parallel to the B field. Do you agree that's not going to cause any force? It's just going to cause a continual drift this way. Then the other one's causing this circular motion. So when you layer those on top of each other, you don't get pure circular motion, you get this helix. Okay, what do you think? So far, so good? At some point, it's getting way, way hard to try and do this stuff on paper and pencil. You're not going to figure this out with paper and pencil. That's annoying, right? Make the code do it. Now, I personally don't like to believe codes unless I can see it in real life, if at all possible. Like I like to see things. So now I'm going to try to go to this down here. Oh, there it goes. Okay. All right. So in this case, just to help you guys see this, if you guys want to scoot over just so you can see it, you can probably see all right. I don't know. You may want to scoot over for a bit, maybe. All right. Okay, so the filament on this should go up to about 7.5. Oops, it's touchy. The anode voltage, I'm going to crank it to about 300. I'm going to give it a minute to warm up. Okay, now I don't know if you can see this very well. This bulb is expensive, all right? This thing is like $1,000. So do you see that glowing? Do you see there's something glowing in there? That's the
Yeah.
filament. Remember when we heat up the nichrome wire, it just gets hot? You can literally boil electrons off of here. And inside of here, this is like that cathode ray tube where there's almost no gas inside of it, right? It's not a perfect vacuum. It's got a good vacuum, right? Can you guys still see that on Zoom?
We don't see
Yeah.
the glow anymore.
Yeah, you can't see the glow, but I mean, you can see this. and
Yeah,
that.
I see the.
All right, cool. Does this make it better or worse? You have a backdrop there.
It was fine, but that's also fine.
Okay, let's leave this off then. Do you see a blue beam there?
Oh yeah.
Is that better? And let me turn this to blank. You see the blue beam now?
Yeah.
Okay, so that's a beam of electrons. Now what I've got right here, this last dial, I'm going to adjust, and I don't know if you can see the numbers changing there. I'm going to adjust the current flowing through these coils. Now we haven't discussed this yet, but the current through the coils creates a magnetic field. Just like moving charges experience a force from a magnetic field, moving charges will create a magnetic field. Sort of like charges can experience and create electric fields. Well, in this case, I'm going to crank this up. And we see a blue beam in there forming a circle kind of ish. Do you agree? Does it kind of form a circle? There's a little bit of a focus issue here. Sometimes we can adjust that, sometimes we can't. Maybe that's a little better. Can you see it slightly better? Or is that worse?
That looks good.
Okay. Now here's the deal. You agree this is a beam of electrons? You agree it was initially moving this way? What direction is the magnetic field that I created? Yeah, which way? What are our choices? Okay, let's start again. Do you agree the charge is moving in this plane here? Let's call this the XY plane, the same plane as the whiteboard. So that's usually the XY plane in all of our discussions. So let's say the electrons are moving in the XY plane. What direction does the B field? Well, it's got to have some component, right? Which way? Either plus or minus K hat. Okay, you tell me. At the bottom, let's start here. The electrons are moving which way? that way, right? It's got to be moving this way because they start in the middle and they go to the outside of the bulb. So which way is V? Well, let's get our right hand out. Figure it out. Which way is it? Can't see it, but we know there's a velocity this way. Right? So what are my choices for B field? You said it. Into or out? Well, let's check it. Right. Is that the way the charges were deflected? So is that the force? No, because it's negative charges. Gotcha. Right? This goes to there, points downwards, flip it because it's a beam of electrons. So the B field created by these coils must be into the page. Got it? All right. So hopefully I've got you enough times with that minus sign. You're like, okay, I got it. Just don't want that to happen to you on test day. So the idea again, when I crank up this B field, we see it starting to deflect. Have you noticed they call magnetic fields B fields? Yeah. So generally we talk about E fields for electric fields and B fields for magnetic. Just to, I don't know, that's what people say. Now what's going to happen if I twist the bulb? What shape will we get? The helix. Remember, if I twist the bulb, you can't really see it that well at all. So I'm going to try and twist the whole apparatus in the dark and hope I don't break it. All right. It's getting hot. You see the helix kind of ish on Zoom? Can you see that at all?
Yeah, we could see it.
You see it kind of spiraling there? Let's crank this all the way up. Whoa. Oh, yeah. Oh, yeah, that's cool. What did I just turn? I don't even know. I hope I'm not burning this thing up. Yeah. Well, if I adjust the focus on this, it's pretty hard to see here. But yeah, there's a little bit of a helix there. Kind of spiraling out. Good enough? All right, just trying to show you that this isn't just some bullshit in a computer that I made up, all right? That was all that was for. Oh my goodness. Let's turn this off, turn this off, turn this off, turn this all off. Okay, done. Now, oh my goodness gracious, where was I going with this? All right, let me turn this back off. Actually, let's do this. Let's hit the lights. What was the point of all that? Oh my gosh, that was page 139. Whoa, that was kind of crazy. We've got just enough time for one more problem. Look at page 140, 28.3. Charged particle moving, it enters a region. And we see it take this circular path or semicircular path, and it's going to spit out. Okay. In this case,
Oh, George said we're still looking at the
that's
bulb.
right. I was testing you. Oh, thanks for reminding me. Thanks. Sorry about that. What problem was this one? 28.3. Oh man, that took a long time to get through the first three problems, didn't it? Oh sheesh. Okay, we got this charge. It's moving this way. At the end, it comes out that way. What does this tell you about the electric and magnetic fields if this is taking a semicircular path? What's that? Well, let's remind ourselves. What's the force due to the electric field? Just remind me. QE. What's the force due to a magnetic field? QV cross B. If you wanted to, you could combine these into one megaforce called the Lorentz force. Sacre oh, garçon, wine. E plus V cross B. That's what we'll do the last week of class. But the idea is, which one of these causes circular motion?
Like that.
A magnetic field, right? If you had an electric field present, wouldn't that screw up the force towards the center all the time? So if you had an electric field here, it would do something and screw up the pattern of circular motion that we saw. So we can see that clearly here, if this thing's going in a circle, I want you thinking about magnetic forces. If you had a problem that had both an electric field and a magnetic field, and you wanted to understand the motion, how could you do it? What did we just do a few minutes ago when we had a complicated motion? We couldn't figure it out.
Code.
Code it. Do you agree? It'd be really freaking easy to say, here's one force, here's another force, add them up and get the net force, and then run the simulation. So in general, you have options now that are just so much better than the ones I had when I was in school. So you're gonna have to basically learn how to code this. So in closing, right, it's time to go. You may not read the book very much. I recommend, at least for this chapter, before Wednesday's class, reading the book. A book, any book, skim it, 20 minutes. Okay, and the reason is we are going to fly on Wednesday, and we're going to finish this chapter on Wednesday. Right, we still got to talk about forces on wires. We got to talk about torque. We've really got a conceptual understanding, and now it's just going to be crunch, 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 and just do a bunch of math on Wednesday. Also, you don't have a pre-lab this week. We're building motors. Come to class on lab on Thursday with your arts and craft mindset ready. Okay, so instead of doing a pre-lab, actually read the chapter for once. All right, and see, I think there's some really good stuff in the books on these. Oh, man. Okay. I guess don't forget, yeah, if you haven't already done so, plan the rest of your semester, right? That the finals week is going to be horrible. The week before, you got a test. Then, you know, I don't know, get your homework done. You want to be doing this homework this weekend, right? You want to ideally be finishing this up this weekend. All right, all right. Any other questions? All right, let's see if there's any Zoomers out there with questions. Any questions from the Zoom crew?
I have a question.
Yep, go for it.
What's that bulb like used for practically?
What's that, what?
The device
Oh,
you use for the.
This
like,
is
field.
used, basically, it's a student demonstration to help students do actual measurements. If I go back to that, let me go to 4. Oops. And scroll down. This thing, I don't know if you could see it, it's pretty fine, but inside of here, there's actually small tick marks. There's a metal grid, and you can actually do an experiment and do the math on it. And that's described here. It's basically a student learning device. That's it.
Okay.
That said, the physics of what's going on here, I don't know if you can see all the metal plates inside of there and stuff. That relates to, for example, a mass spectrometer, which is on the next page. If you want, the physics of this is nearly identical to the physics of a mass spectrometer, which is on. Sorry, let me just get you the problem real quick. You have your workbook handy? Can you see
I
page
think it's
141?
142. Oh, 141.
Yeah, something like that. 28.6
Yeah.
shows
that's
you
the
how
one.
to do the mass spectrometer. And so we see that when you have it's a very popular problem. It's in every physics book because it uses both electric fields and magnetic fields and forces, and you have to think a lot. So if you're interested in kind of the practical applications of going further with this, that's, I guess, where I would see it going. Is
I
that
see.
cool?
Yeah.
Yeah, yeah. All right, cool. Others? Did you guys have any questions?
Questions are related, like electricity magnitudes, and you just add them up. to get the-
Yeah, I mean, yeah, exactly. You could just do a net force, force 1 plus force 2.
No, 50 is that simple.
It is that, so that's
So
what's
that's
cool about
electromagnetic.
physics 1, right? You just learned, how do I get the net force? You just add them up, superposition of forces, so to speak.
Okay.
How do you get the net field? You could add up electric fields, right? You get the electric field from different pieces and add them up. Same will be true for magnetic fields.
Okay.
Cool?
Cool.
Yeah, good? All right, later. Yeah. Yep,
See you later.
yep. Have a good
See you
one.
later, Joe said.
Later. Study hard.
Always.
All right, later. See you on Wednesday.
Yep, sounds good.